Chapter for the brief introduction of this paper. Yes, this is like a automated framework for geo replication, which means that if you give a non-replicated serializable code and the schema to the framework, it will actually make it geo replicated. So let's understand like what is geo replication. As we all know, it is a type of data store where the data is stored distant in multiple places, like in multiple physical locations. Why do we need it? As the app is growing, there are so many users across the globe who are using the app, and the app holder should make sure that every user is every app is available to every user. So that provides low latency responses and quality internet services. And there are some challenges, as we know, like data consistency. How can we make sure that the data is consistent across the servers, across the data centers, and the cross-site coordination, where they could be slow and expensive at the same time. So the existing cross-site coordination systems actually take a unique serial or unique ID for each and every entry across the servers. And that became expensive, and then they actually had this partition, like key partition strategies, where they have unique IDs for each and every partitions across the servers, making sure the data is coordinated or in sync with each other. And there are also like maintenance and other costs such as storage and how to maintain when natural calamities occur or whatnot, like regular geo-replication maintenance issues. So this goal of the paper is to develop this end-to-end framework to automatically deploy and take care of all the challenges and also the existing problems by taking this non-replicated serializable code and make it into a geo-replicated application. So this geo-replication happens only with the non-replicated serializable code. So most part of the static analysis goes into making sure that it is non-replicated before and is serializable. In order to actually understand their approach, they gave us like 3 examples. If you look at the first example here, there is this user called Bob, and one person is trying to update the location NYC to London, and the other person is trying to update NYC to France. And the system should be able to automatically grab the final update. For example, it could be in a millisecond difference or a nanosecond difference. They should be able to find the updated update. So, but here it could be different. Like if the other person could see other person's updates for the same account, so then there is no convergence here. And the second main issue is, even though the convergence happens, like if you take the withdrawal request here in the second example, for the same Bob account, somebody is trying to withdraw 50 and somebody else is trying to withdraw 60, but we do have an invariant, or the semantic is the balance should not go less than that certain amount. So it should always be greater than or equal to, like you have to make sure that the balance is greater than or equal to 50 or 60, the amount of that you are withdrawing. It shouldn't go negative at all. So after performing one operation, the other person might not know the effect of that operation and still think that the original amount is there, and perform the second operation, which will actually give them -10, and that is an invariant fail. So in not only convergence, they also have to make sure that the effect of the particular request after it has happened. So if you take the third example where the requests are commutative, which means that withdraw and deposit are both commutative, in a sense you can do withdraw first and deposit later, or deposit first and withdraw later. Finally, the amount will not change. So for these kind of systems, you don't need to actually do any semantic or restriction checks at all. So the main idea is to find the possible scenarios where these kind of conflicts occur and make them serializable, and run through a protocol where they can be acceptable for replication or not. So digging deep into this AutoGR framework, this is actually using two different phases. One, I would say static and runtime. And the first thing is the RIGI, which is a naval static analyzer internally using G3 theorem prover developed by Microsoft. What it does is it takes the app codes and schema and like generates these formulas by all possible paths. So it travels through the all these possible paths in the program, and then develops these formulas and see if they can make these formulas serializable if they are conflicting with each other. And then OLSIPO, an existing coordinated system, which actually is a normal Paxos-like protocol. It runs on a Paxos-like protocol where it can tolerate up to F failures, and it makes sure the replication happens. So since that is the dynamic part, and RIGI is the static part, which actually does all the pre-checks and getting all those restrictions for the runtime process. So we will talk about it more in the later slides, but I just wanted to give you a general idea, like what this auto framework is trying to solve and do. So here we can see in detail. So this is the static part, and this is the dynamic part. In the static part, we have RIGI, developed by them, which is a static analyzer, which means that it takes all these codes, develop a control flow graph, which we'll be discussing later. And within that control flow graph, it passes through each and every condition to see if the conflicts are, if the restrictions are conflicting with each other. And it finally gives some serializable restrictions. So by the time it is serializable, then the program is obviously geo-replicated without any conflicts. So that's the main purpose of generating these restrictions. And once the restrictions are generated, then it goes to the runtime process where OLSIPO comes into picture, running this Paxos-like BF smart protocol across the servers and does the replication. So if we look at the static part in detail, what this RIGI is having are three phases. First thing is the collector. Second thing is the dblib in the G3PY code. In Python, and then there is this checker which actually checks the restrictions if they're on certain basis. So first, the collector actually inspects the source code and identifies if there are any side effects that could be generated from the code paths. So for that, obviously, it will have to create a graph kind of tree-like structure and then traverse through each and every path to see all the effects, like what happens if the program goes into this path, what are the side effects, and things like that. Once the paths are generated, then it uses this DB library to represent that whole effects into C3PY code form of query. So generally, we know the SQL features are like insert, update, or delete kind of queries. But it translates that everything into Z3PY Python version, which will not have all these like all these standard SQL queries, but something different that is understood by the Z3PY code. And once those side effects are generated, those are sent to the checker where the actual checking happens. So let's look at the collector first. So to talk about the collector, we need to understand how a control flow graph is used. For example, here is a simple program that is actually checking if two input integers are equal or not. If they are equal, it returns 1. If it is not, it will return something else. I mean, if they are completely opposite, it returns -1. If it is different, then it will return 0. So I actually took an example of if else conditions, but you can actually take loops, then the tree would be pretty much cyclic and it would just rotate in a loop. So first is the input node, like the initial node is this one, and then the first if condition is met at this point, it will check. So there are two possibilities. One, it can either go into that if condition or go to the next, like to the bottom of that if condition, which is another else if. So if it goes to the into the if condition, then it will return the value which is given to the out node, like output node. And if it is not, it will go to this else if statement where it has again like if else statements. So if it goes into that if condition, it returns -1. If not, it will return 0. So both are the outputs again. So they will be given to this output node. So this is like a simple control flow graph of a program. So this kind of control flow graph is generated for the entire program. No matter how many lines of code they have, like they are generating this control flow graph for the whole program. And they will traverse through each and every path and find out the side effects. So if this is happening, then if this particular condition is met, then what is the effect? So for example, here is a condition and then the side effect. So here is somebody is getting the amount balance from the some checking account, and the effect will be either the amount that they are trying to withdraw will be either, I mean, the amount that they are trying to check will be either greater, like deducted from the balance or added to the balance. So it is like a logical or some kind of atomic formula, which is given to the Z3 solver to actually get the restrictions out of this effects. So once these conditions and side effects are generated from the collector, now they are actually given to this DB lib, where all these effects are transformed into a Z3PY specification. For example, here is a create table query, and that is the right hand side is the Z3PY specification of create table. So they have keywords like declare or array specifications for all the keys, etc., for all the columns, etc. So once the Z3 PY specification is found, then they are all given to the RIGI checker, where they actually check two types of checks. Well, first one is the commutativity check, and the second one is semantic check. So commutativity check, they are trying to make sure if the operations, if they take two operations, they should be commutative to each other. For example, like our withdrawal and deposit queries, like they can be happened in either direction. So then they will pass the commutativity check. If it is not, then they will have to make the task conflict and try to serialize those conflicts. And the semantic check is to ensure the non-replicated serializable code is in its geo-replicated version is correct or not. That, for example, the FX after the condition is met is not violated by the another condition and its effect. So after this, the RIGI checker will give you a series of restrictions which can now be replicated and performed onto the app store. So that happens through Olisipo, and we, like previously discussed, like Olisipo is a runtime library which performs a cross-site coordination service. It could be either time management or time stamp syncing, because that plays a crucial role when they are trying to deal with non-convergible conflicts or restrictions. Once the data is passed through the cross-site coordination service, it will actually run a BFT smart consensus protocol, which can also tolerate like F failures like Paxos, and see if they will pass that each restriction or not. So if the restriction is passed, it will actually go into the global partial order. If it is not, it will be not considered for replication. And this is not like a fully consistent protocol like Raft or anything, because it is only based on the restrictions and nothing else. So
hey, Lakshmi, can you pause for a second?
Yeah.
Yeah. So the coordination service, right? That's like, what is the restriction, right? Just a set of rules, correct?
Yeah. Yes, Professor.
So it's a rule that says, for example, withdraw operation, it needs to know the latest state. So before you run the withdraw operation, you need to, essentially synchronize, right? So,
yes, based on the
operation will have a restriction that says, it essentially conflicts with everything, right? Or with everything that updates the balance. Well, except yeah. So you don't know there are like multiple withdrawals, so you always need to synchronize every withdrawal. because it may conflict with other withdrawal, right?
Yes.
So
Depending.
the coordination service, it should take those restrictions and say, oh, I see the withdraw operation. Let me, ensure that I can run this withdraw operation. Let me, actually synchronize, like make sure things are synchronized at this point, right? So withdraw operations, they need to be partially ordered with any other withdraw operation.
Yes, Professor. Depending
right?
on the type of restriction,
Yeah.
they are actually checking the timestamps to make sure that the data is the latest write is picked.
Yeah, and the replication, everything gets replicated at the end, right? Because we still need, to have the copy of everything everywhere. It's just that how you replicate, right? So if you have the restriction, if you have this withdraw operation, you need to, partially order it with all other withdraw operations. That's, yeah.
Yes, Professor.
Yeah.
So if I might chime in, it seems to me that first of all, there's operation replication, not value replication. Because if you're commutative, you're trying to allow the commutative operations to flow. It also seems that without bounding the scope of the data and without bounding the kinds of operations, you end up in some very weird questions about transactional changes. I'm doing multiple operations against multiple things, and are they all there or none of them are there? And, traditionally when you're doing add and subtract, even if you have a centralized system, the interaction of the commutative nature of add and subtract with reads and writes is disruptive. I mean, literally in 1988, at Tandem and Nonstop SQL, Franco Pozzolo and I built out this thing to do escrow locking. If you did addition, subtraction in SQL, it would log plus or minus, and then it could really be massively concurrent until somebody decided to read the value and you shut everything down, figured out what committed or aborted, and then you see it. It seems to me that this is not addressing a myriad of issues, even though I think it's kind of cool to think about programmatic analysis to identify potentially commutative operations, but I'm going crazy as to why this was at VLDB. Go ahead.
Yeah. So this is never looking at specific operations, right? It will never look at each independent instance of each operation. It strictly looks at the operation types, right? So with the static analysis, you can say that withdraw operations they conflict with our withdraw operations because of this semantics check, right? You have to check the balance, and the other withdraw operation can actually screw up your balance. So you're like, you cannot run two withdrawals concurrently. It's not doing like it just says that there is a possibility that withdraw operation may screw you up. So let's create this restriction and let's partially order every single withdraw operation with each other. So in that sense, it's very dumb, because it just says, okay, there is like, even if there is like a super remote possibility that you can screw up, it will put this restriction on everything, like the entire class of operations. So that's kind of one thing. And as far as reads, I have a lot of questions here as well, but I can probably should talk a little bit later about this, like after we got through the evaluation.
Yeah, let's let Lakshmi. She's doing a great job. This is great here in the explanation. So I'm thrilled with your effort. You should continue.
Yeah, I really was not able to get into how they're actually doing certain stuff, but this is like a broad picture from the top. Okay, this is what they have, like the cross-site coordination service. As far as we know, we can only think of it as like a timestamp checker for maybe all restrictions or some restrictions. That is not 100% sure, but it is actually doing some kind of checking to make sure that the latest data is pulled and which is actually sent to the replication. And how effective the non-replicated ones are going. So there are some protocols like where if a particular request or if a particular user request is not replicated, then it actually goes back to the queue again for the request. So some protocols do that, and some protocols just ignore it for the user to try again. So there are some things that I really don't understand, like how that is actually managed. But yeah, so this is like so OLCPO is like has these two parts: cross-site coordination service and the replication. So coming to evaluation, they took the 4 applications such as Small Bank, which is like a small banking application, Rubis, and Seeds, reservations, and Health Plus. So as we can see, the code base for Small Bank to Health Plus is gradually increasing. Like Rubis is 9.8K, Seeds 5.0K, and Health Plus 15.7K. So once the control flow graph is created, they were like, this is the analysis of the static analyzer RIGI. So the loop operations are like 40 operations in Health Plus because it has so much code base, and it could have had so many internal complexity. And the conditions generated, these are like 1,113 for Health Plus. So since the conditions are more, the side effects are all more for Health Plus compared to other applications. So their geo replication is happening at 3 places. One is Asia, US, and Europe. They do have a manual analysis, like they completely did everything manually, like went to the control flow graph and found the restrictions. Everything is done manually from their code. And the optimal version, like AutoGR or OPT, is the optimized version of AutoGR, where they actually incorporated 2 optimizations. One is the automatic timestamp checkers to decide or pick the latest write to the final value in the cross-site coordination service. And the second thing is the existing, so the checker has an additional feature to check if the IDs of the side effects are unique or not. That way they can make sure that the side effects are as unique as the requests sent to them. So as you can see that the average latency observed by the users at different sites for all the apps except for Health Plus, because they were not able to do manual analysis for that big code base. The manual and optimized AutoGR version is almost the same for each and every other 3 applications, and in comparison with Strong, which is like their version of strongly consistent application, they have like high latency compared to the AutoGR optimized or AutoGR normalized ones, which makes them prove that their version of AutoGR OPT is very very effective in terms of latency. As in figures, I think it was like 39.8% to 61.8% of latency efficiency is observed in this process. But it could be because of the app itself, because some applications depend, like the application is dependent on how many restrictions it is going to get, and how much time it is going to take, and how much cross-site coordination it requires. And especially if not all the requests are going through the cross-site coordination, then it's obvious that some requests take long time and some restrictions don't. And among the 4 applications, the latency improvement is for Rubis, and the worst is for the Seeds. And because of because of the restrictions that could be very small for Rubis and large for the Seeds. And if you look at the normalized throughput, so the throughput, there are like, this is normalized version of, this is normalized to the Strong version of the whole configurations, like all the 4 configurations. And AutoGR OPT actually performs the best of all, achieving as good performance as manual. Again, it depends on the restrictions, throughput also. It achieves a speed up ranging from 1.39 to 2.12 times compared to Strong. So that's what their evaluation says, like the AutoGR is having high throughput and less latency.
But what's the characterization of the apps which allows this commutativity and allows this advantage? I mean, strong, as I'm hearing it, is a classic read-write consistency, and they're going slow because they have to if you only have reads and writes. And the trick here is to try to identify commutative operations and to modify the code to take advantage of the commutative operations. And I'm assuming they're operation logging so they can be reordered across the replicas, but they're not quantifying the nature and the characteristics of the app, at least not that I'm hearing.
I think there is a lot of details actually in this aspect is missing. I mean, they provide these types of apps, and I believe you can follow the references if you like really nitpicky. But one thing that caught my attention that in my opinion was a kind of a big red flag. Most of the operations that they do are, and Pat, you're gonna love it, they're reads, okay? It's just like reads in the state. And like 85% in those benchmarks. And again, I believe like when they do those reads, they say, they have like strong consistency or whatever. They're doing local reads. So it's not even like a strongly consistent read, by any definition. They read a local copy.
The definition of consistency is way up in the air in this world.
Yeah.
And they're just basically saying pretty good. Let's go get something, and it doesn't matter if it's right or wrong or stale or whatever.
Yeah.
And sure, I can read that stuff fast.
But yeah, like if you just read your local copy, if you don't produce any side effects, then you can go really fast.
But the question is, can they identify from the program when that will be innocuous and behave identically? And I've not understood when and where and how they could do that. Did that make sense?
Yeah. In the paper, they mention some. Their specific thing that they try to achieve is to make sure that their replicated version doesn't end up in a state that's impossible in a serializable version. So they try to make sure they preserve the semantics, and supposedly all of this magic is done with the RIGI static analyzer, right? By analyzing all of those, by finding all of those dependencies. Now, coming back to your initial question, like some operations have a lot of these dependencies and will require a lot of synchronization and will inherently not work well. And some operations will work well, right? So how the benchmark, how the evaluation proceeded with like how realistic is this? Did they pick on the good commutative operations that don't have a lot of semantic checks that they need to slow them down to generate those restrictions, or so that is that's up in the air, to be honest. I don't think the paper does a very good explanation on that.
I didn't read the paper. I should have, but everything in me is screaming worries.
Well, yeah, it's VLDV 21. And I think their manual one is them pretty much following the other paper, the POR consistency.
Yeah.
And doing things manually. So in that regard, at least in what they tried, they achieved kind of similar results. So that's nice. But how nicely it translates into the real world, not entirely sure here.
Yeah, I also like the idea of the static analyzer giving. So it might take so much time depending on the application that they are going to test it for. But the idea, since it is static, they could do it, or they could spend as much time as they want. And they also claim that having the same solution programmatically done will take a lot of time, and it could be more error prone. So that's what their claim is about the static analyzer. So the idea of getting all these restrictions, I think, is interesting, but once it is going to the runtime environment, I'm not sure how, or if it is compatible with even more efficient Lucifer version, or I'm really not sure about how that will be working. And yeah, so the summary is this is the auto framework for deploying non-replicated serializable applications as Geo Replicated. It adopts restriction-based consistency model, and it may create false positives when there are complex loops, even though how effective their independent loop property is to find the independent paths in those loops. But it could still provide some false positives, and the paper claims that the false positives are not affecting the performance in any way because it is not giving any false negatives. And yeah, it provides low reasoning cost and optimal performance with little manual effort. And while I was in a discussion with professor, like they mentioned that the average round trip latency between any pair of 3 sites, they took Asia, US, and Europe. It ranges from 157 to 169 milliseconds. But it's really interesting that their latencies are way less than that. If the minimal round trip time is 157 to 169, it could be at least more than that or something like that.
Well, and that's implying that they're doing local transactions and assuming all is good. And then that's implying that their restrictions are sufficient to make you not have these applications rejected. And there's no way in hell I believe it. What are your thoughts? What do you think, Lakshmi? You read this in detail and you put this nice summary together. What did you think?
I feel like they didn't have